Okay, welcome back to school, ELE112. This is ELE112 on steroids, coming to you live online for the first time in the history of MCC. You've been a part of something terrible, but big changes. So welcome aboard. In the first week of return, April the 6th, I showed you some information indicating that we would start in Chapter 8 and cover sections 1, 2, 3, and 5. This video in particular only covers sections 1 and 2, and it is titled appropriately. I want to keep things small, quick, and manageable so you can understand where we're going with what we're learning. Future sections could get a little bit daunting and heavier, and I'm going to try and keep things flowing as smooth as possible. Okay, so let's recap. Back in the day, we used to talk about ohm meters. We used to talk about oscilloscopes. We used to talk about how loads have resistance. Loads have impedance. Resistance is the simple version of the deal. Once you throw capacitors, inductors into the mix, you have an impedance. So let's use that word. The voltage source, which is what is discussed, and the current source, which is discussed in section 8-2, the voltage source is taken for granted. You just simply hook your circuit up to it, and you think it's going to work. Well, usually. Voltage source, if you look at the top of your paper that you're seeing right now in this video, is a principal type of energy that's used in electronics. So it's important to understand exactly what does it look like. Is it like an ohm meter? Is it like 10 to 20 mega ohms? Is it like that? Or it's different? And what we're going to find out that a voltage source's job is to provide constant voltage to something that's plugged in. No matter what is plugged in, we want to keep that voltage constant, even though the things we plug in can change, and that becomes very important. If you remember with an ohm meter, we got away with hooking it in parallel all over the circuit because its impedance was 10 to 20 mega ohms. Well, look at figure 8-1. An ideal voltage source has no resistance. In other words, it's just a battery. You hook a load on it, like you see there in figure B of 8-1, and you hook a load out on it, and the voltage is received by the load. But I'm here to tell you that in figure 8-2, a practical current source is a different thing. The thing that's sitting on your bench in the class has a series resistance tied to it called RS, and its value to be useful as a voltage source is that it is a small value, 5 ohms, 10 ohms, something small. If it starts getting into the kilo ohms range, it starts affecting circuit performance that it hooks up to. In other words, this internal resistance steals voltage from the source. So what I want you to get out of this first picture, and then, there's minimal calculations out of this first two sections. When we get into 8-3, we'll do some work with the voltage sources. But right now, I just want you to get out of it that an ideal voltage source has no resistance, while a practical voltage source has minimal resistance. Okay? That's like the 10 to 20 mega ohms of an ohm meter kind of a thing, except a very small resistance. When we get to current sources, as you might expect, it might be a different amount of resistance coming out of a current source. So let's take a look at a current source. A lot of you haven't had experience working with them. Suffice to say, there are devices out there that act like current sources. For example, some transistor circuits are used to provide current to electronics. So a current source is another type of energy that provides constant current no matter what connects to it within reason. Okay, we will do some calculations, and this is a different kind of beast. We're not used to it. Suffice to say that in Figure 8-4, your current source, theoretical current source, your ideal current source, located on the screen, is the unloaded Figure A. And the resistor that you don't see is because the resistance is infinite. There is infinite resistance on that device. So, as such, we show RL over here on the right. The load gets connected, and ideally, there's no other resistance out there. And the current source, which is this object circled in black, if I told you that it was 5 amps flowing, the load would get 5 amps. I changed the load. I put a 1K, I put a 2K, I put a 3K, I put a 4K in there. Guess what? The same current, for example, if it was 5 amps, and I changed the load to 1K, 2K, 3K, the same current is provided to the resistor. This is kind of hard to believe because you're used to using power supplies. But the power supply is in the same boat. The power supply needs you to hook up anything you theoretically want, and you get the voltage that you need delivered to the load. Now, practically, a current source does have resistance. You see it there circled in yellow. That resistance for the current source to deliver all its current towards the green line and around is going to need to be extremely huge. You'll remember back here in Figure A that I talked about the resistor that sits between there is essentially large, like air. The resistance of air is infinite. So the ideal current source has infinite resistance, while the practical current source has huge resistance built into it. Okay? Are you with me so far? Fantastic. Now, the last 2 pages of this presentation are simply looks at the voltage in the current source. These are not really a big deal. You know, you're looking at a series circuit there, which has a battery, a power supply, and it has an internal resistance sitting in series with the battery, like we discussed in section, in the slide 1 of this section. So when we hook a load up, now what they're doing here in this example, which came right out of your book, it says, find the voltage to the source of the source with the following load values. So they want to know how much voltage out reaches this resistor right here, given that there's a small 10 ohms sitting inside the battery that's essentially stealing voltage. Okay, so when you run through the calculations using something simple like the voltage divider, you can see that out of the 100 volts the source is capable of giving, only 90 volts gets out there. So where's this other 10 volts? It's consumed. It's heat power dissipation, basically. Now, if we plug in a load of 560 ohms, we get 98.5 8.2 volts. It went up because what I failed to tell you was, if you look, there's only 100 ohms in that circuit. This is problem 1. Problem 2, they upped the 100 ohms to 560, meaning there was more voltage on the load. The load was larger than the 10 ohms by a long shot. And in this third example, where we take the 1,000 ohms and we jack it in there, look what happens. We get almost all of the voltage delivered to the resistor. Isn't that special? So, what have we learned from this slide? Your battery has internal resistance which drops some voltage as you plug things in. So, if you plugged in a 100 ohm resistor across your power supply in your lab, you might have to dial up a lot higher to get 100 volts delivered to the load. Because if you only set your source at 100, then you plug in, it's only going to see 90 volts. Whereas if you change your load here and drop 1,000 ohms in there, or 1K, then 99, essentially 100% of your voltage reaches the load. Okay, last but not least, the current source, which has an internal resistance built into it right here. We connect the load on the outside. When the load is really, really small, okay, compared to this resistance of the source current, then all the current gets here, all the current, which is about 990 milliamps using current divider. Could have used, well, actually would have been hard to do Ohm's law because you have a current source, not a voltage supply, and this is a parallel circuit. So we had to use current divider. And if we raise the load, now the load approaches the 10,000 of this resistance right here. It gets a little closer, which means that there's a bigger division of the current and more of it will drop into the RS resistor circled in red. Now, if we make the load 1,000, even more current will go, less current will show up across the load. So what you have is, in a current source, its resistance is huge, and the bigger the load gets ohmically, the lower the voltage the current gets through that load resistor. Very interesting. Let's move on to Chapter 8, Section 3, and we'll talk about using a few of these in a different way. Thank you for listening.